Hello everyone, welcome to the next lecture on the stochastic process. Today we will discuss the concept of Poisson process. Myself, Dr. Garg. You can simply follow my YouTube channel Dr. Harish Garg, where you can find various videos on the probability and statistics. So in order to understand the concept of the Poisson process, there is a need of understanding the concept of the counting process. So firstly we will try to learn what is the counting process. After that we will see what is the Poisson process, what is the pure birth process, what is the arrival and the inter-arrival times, and finally we will try to solve the examples related to these four concepts. So since we are working on the counting process, so you must have to understand firstly what is the stochastic random process. And you can see all these previous lectures are available in the playlist probability and statistics channel name Dr. Harish Garg. You can simply follow this one for finding the various on this Markov chain. Now any of the stochastic process is said to be counting process when if it satisfies the certain property. As the name suggests, is a counting. So if I say if this NT will count the total number of the events occurring up to the time t. So if I say, or you can say, since it is a total number, so it can never be negative, because the total number, it can never be negative. Second property is it must be the integer value, it must be the monotonically non-decreasing, and the difference of this nt minus ns represents the number of the events occurred in the interval s comma t. Means if I say there is an interval s of t, there is occurring of some events, say n of s, there is occurring of some event, say n of t, then the difference between nt minus ns represents the number of the events occur in this interval. Once you know these four properties, then the process is said to be counting process. And this counting process is said to be independent and stationary when if the number of the events that occurring in the disjoint intervals are independent. It means if you have defined this kind of the interval s1, s2, s3 and so on, then the number of the events occurring in this interval, say n1, 2, number of the events occurring in this interval, that is n2, 3 and so on, all are my independent. And what is the meaning of the stationary? Means if the number of the events in this interval is same as that of the 0 comma t. What is the meaning? What is the length of s plus t? What is the length of this is small t. So similarly, what is the length of this is again small t. Or in other words, if I say n2 minus n1, this is the length is my 1, which is same as that of 5 minus 4, because you can see the length of 5 minus 4 is 1, the length of 2 minus 1 is 1. So similarly here you can see s to s plus t, the length is my 1, length is my small t, and the length is again my small t. So whenever it has follow the same distribution, then we call as the stationary increment. Now in order to understand this counting process, we will try to understand what is the phenomena is there. So there are so many ways you can define this counting process phenomena. So let's a very simple example. Suppose we would like to model the number of the events that happened completely at the random rate lambda. We sometimes this called as say intensity or called as the rate of the arrival. So what we can do is say if I start from the event at a time 0, then we consider there is no arrival at the initial step. So that means this is the n of 0 is 0. We discretize this complete real line into this small intervals, say delta, then of 2 delta and then so on. We divide this half line, that is 0 to t, into the tiny subintervals where delta is a very small number. Then what is that? If I say consider this is my nth or kth interval, it can be written as k minus 1 delta of k delta. Like of this is the first interval, 0 delta, 1 delta. This is my third interval, so 2 and 3 and so on. Clearly says that whenever delta is very small, so what is the total number of the intervals? So what is the length of this? Length is my delta. Length is my delta. So the total is my n. So you can say this is my complete here, or you can define the n is approximately t upon delta time slots in this interval. Now how you can define that? Suppose you want to calculate the number of the events, number of the arrival events occurring here. So what we can do is we can simply toss a coin with the probability p. P is nothing but my here. Then what is the meaning of that? If the coin is landed up a head, we assume that it's arrival occurring. If coin landed up as a tail, then we assume no arrival occurring. So what is the meaning? So I can start from here. This is my first interval, this is my second interval, and then so on. Let's say I firstly toss the coin and tail appears. So it means there is no arrival. Second time again assume that there is a tail appears. So again there is no arrival, and so on. So what is the meaning of that? The first arrival is occurring at this interval. This is my first arrival. This is my second arrival, and so on. So the first arrival is occurring after the time t1. Second arrival is occurring at the time t2, and then so on. Then we can define NT, that is the number of the arrivals. In this particular example, number of arrival is the number of the heads from the time t is equal to 0 to the time is equal to t. Then clearly says that since it is a finite length, so NT represents the number of the heads in this. So how many in this up to here, how many heads are there? 3. So I can consider n is my 3. But if you consider from 0 to t, how many heads are there? Let's say these are my n number of the heads. So since p is my probability here, n is my finite, so it follows my binomial distribution. So what is the mean of this binomial distribution? We all know that mean is np, or you can say this is n into lambda of this. So I can substitute the value of the n here. You will see this is my lambda. So what is the meaning of that? As delta approaches 0, that means if this length is very small, what is the meaning of that? It means n goes to the infinity. Once n goes to the infinity, it means it follows the Poisson distribution with the lambda rate is here. So what is the meaning of that? The counting process will follows the Poisson distribution with the parameter lambda t. The number of the arrivals will follow the Poisson distribution as the arrivals interval is very small. If I look at again here, so consider the non-overlapping interval. So say this is my first interval, this is of the first class, this is the second, or you can say this is my first interval, this is my second interval, and so on. Then clearly says that the number of the arrivals in each intervals is determined with the help of flipping the coin. Since tossing or flipping the coins are always be independent in nature, hence these are my counting process is my independent increment. Now based on this counting principle, we can define the Poisson process. So one of the most important type of the counting process is the Poisson process, which is defined by Siemens Poisson. It's a French person, is born in 1781. It has a wide applications, and it is generally used in the scenario where we are counting the occurrence of the events that happens at a certain rate but completely at random. For example, look at that. The number of the snake bites in a city, always the frequency or the counting of the snake bites in a city is very small. That is, it may happens that, but it's a very small number. That is, a delta is approaches to the 0. Number of the car accidents in a particular city, that's also very small rate are there. Location of the users in the wireless networks, timing of the earthquake is very small. Outbreak of the war is again a very happens at a certain rate but completely at the random. So all are the applications of my Poisson process. Now based on this here, there are the two ways we can define the Poisson process. The first one is the axiomatic way. If I consider lambda is any fixed number, or you can say lambda is my intensity, then the counting process, that is n of t, is called as the Poisson process if it satisfies these three properties. The first one is at the initial level there is a counting process is 0, it has the independent increments, and it follows the Poisson distribution. Another way is, in order to define the infinity description, we need firstly a definition of the O notations. Or clearly says that when you consider lambda is 1, what will happen here? It is nothing but my e raised to power minus t raised to power n over n factorial. What is that? This is nothing but my standard Poisson process. Now, in order to define this second definition, we need the concept of these small o notations. What is the small o notation is? If you consider any of the function f is said to be the notation h. So if I consider here as a h, then it satisfies this property. That is, whatever the function of this f of h divided by h is 0, then we can say it's a small o notation. For example, if I consider the function is x square, Is it O notation? Clearly says that f of h by h is my 0. So hence this is a O notation. On the other hand, if I consider the function f of x is alpha x, where alpha is non-zero, then clearly it is not a O notation because this property not satisfied. Based on this O notation, we can define that's the second definition of the Poisson process. The first two properties are similar. Here that is called as the stationary increment. The third one is, what is the meaning of this is, that is a zero arrival. Probability of the occurrence of the zero arrival is 1 minus lambda t, and here is the order, that is the O notation. What is the probability of the occurrence of the 1 is lambda of t, and more than of this is a 0. Clearly says that when this intensity rate is considered as a constant, we call as the homogeneous, otherwise called as the non-homogeneous. Another concept is we can easily see that this from this exam way definition we can simplify this infinitely description definition. What is the meaning of that? By considering these assumptions, we can deduce these properties. Clearly says that the first two properties are automatically satisfied here. Our target is to hold this one. So that's very simple. We can consider NT is the counting process or the Poisson process with the intensity rate here, and we consider a very short time interval t, or you can consider as a delta, but here I consider as a t, a very small interval. Then the number of the arrivals is defined as the n of t. So by the definition of this here, the number of the arrivals will follows the Poisson distribution. So we can substitute here, if I compare this, I can substitute n is equal to 0 here, I can substitute n is equal to 1 here, and then so on. We will try to devise this one. So I can substitute n is equal to 0. So if n is 0, this value becomes 1. This is my 1 here. Now I can expand this value. Clearly, since it is of the length small t, if it is a very small number, then this value will ignoring the higher and the second power. So this part will goes to my order of t. Why? Because clearly says that if I consider of this, it goes to the 0 as t approaches 0. So it means this function will satisfy the order of t. Clearly say that what is the probability of occurrence of the one arrival? I can substitute here as n is 1. So this is my 1 factorial 1, and here again I can expand the value of the e raised to power minus t here. I open this bracket. Clearly says that this higher power we can neglect it. It is here. Similarly, when you consider lambda is 2, then it is of the order of t. Now the next one is, we can define the arrival distribution theorem, or called as the pure birth process. What is the meaning of that? If the arrivals are completely random, then whatever the distribution functions of this, it follows the Poisson distribution. Or in other words, the probability of this counting process, or called as the Poisson process, will follow the Poisson distribution. The proof is very simple. I can consider this number as of this. I simply take the notation of this. What is that? If I consider here as n, then this is my n. Whatever I have written here, this is my here. Then we can define the t plus h to be here. Depending on this value of the n, either n will be 0 or n will be greater than or equal to 1. I can define the two cases. What is the meaning of the n0? It means there is no occurrence are here. That means here 0 events, then there is no new arrival, still there is a 0 event. So what is the probability of this? What is the probability at the t plus h? That means the probability occurring at here. So since n is 0, no units occurring at t is equal to 0, and there is no new arrivals at time. What is the difference is h. So what is the probability of the no unit occurrence? That is a p of 0. What is the probability of occurrence of the no arrival? That means no arrival, that's a 0. So I can take this value here. Now you can open this bracket and rearrange it. We can written like here. Take limit h approaches 0. So what is that? This part will goes to the 0 by the own notations, which can be written like here. Now what is that? You can simply integrate that. This is p dash 0 over p0 is minus of this. You can integrate them. You will get this expression. Now how you find the unknown number c? You can take as a initial conditions p of 0, that's initial probability is 1, rest are 0. We can substitute this value here. What is the value of this? So this is my 1 c e raised to power 0. So what is the value of c is my 1. So I can substitute C is equal to 1 here. You will get the P0 is this. Clearly says that this result holds for n is equal to 0. So clearly say that when n is 0, this results hold. Second case is whenever n is greater than equal to 1, then there are the two cases. What are those cases? Firstly case is when you consider initially there are the n events and there is no arrival, so that the total becomes n, or if there are the n minus 1 events and the 1 arrivals, then there is a n events. What is the probability of this case? Probability at t is equal to this is n events and there is a no arrival occurring. So when there is no arrival, this is the probability. Probability of this is written as here. Corresponding to this is the probability of n minus 1 events and there is a 1 arrival probability. So we already defines that what is the probability of the 1 arrival. This is my here. So this is my here. Now since both the events are disjoints, so we can write the total probability of this plus of this. Now again we can open this bracket and we can rearrange it. This can be written here. Then take limit h approaches 0. This part will goes to my Pn dash, that is the derivative, which can be written as here. We can rearrange them. We can multiply this by e raised power lambda t and we can written here. Clearly says that I can written this part as of this form. Now we can take this is the result hold for n is greater than equal to 1. So what will happen if n is equal to 1? We can substitute here. What is the p of 0? We already derived that p of 0 is my here. So I can substitute p0 here, which is this one. Now you can integrate on the both side. You will get this. How you find this unknown constant? So because we know that p of 1 is 0 is my 0. So we can substitute here. So what is that? This is p of 1 0 is 0. This is 0 plus a. So a is my 0. I can substitute here. Clearly say that the result hold for this one. Now for n is equal to 2, I can substitute n is equal to 2 here. This is my p1. I can substitute the value of p1. This will be cancelled out here. Again you can integrate on the both side. You will get this expression. Clearly says that b is 0 by using this initial condition. Similarly we can define n is equal to 3 here. This becomes my p2. We can substitute the value of p2 here. We will get here. Integrating on the both side with respect to the t, we will get here. Again p of 3 is 0. What is the meaning of that? C is my 0. So clearly say that and here p1 is this, p2, p3. In general we can write like of this. Next result is if you have the Poisson process, then the number of the events in any of the time intervals is follows the Poisson distribution. So that's again a very simple. Our target is to find this expression. So first of all, I can write this because Poisson process is my stationary process. So we can write it as here because I can write this expression as of n of the what is the length is? Length is my t. So I can write this number as n of 0 also. Sorry, n of this is also because you can see the length of this is also with a t. But we all know that what is the n of 0 in the Poisson process? That is my 0. So I can substitute here. It will be my this. So by using the previous result, we can write as such of here is the simple proof of here because of the stationary increment. Now another concept is that is the arrival and the inter-arrival. What is the inter-arrival is? The time between the two consecutive arrivals. Means if the first arrival is occurring at the time t1, second occurring is at my t2, then the time intervals in between them, that is a t2 minus t1, is called as inter-arrival time. What is the property of the inter-arrival time is? That is if you have the Poisson process with the intensity rate is my lambda, then inter-arrival times follows the exponential distribution. That's a very simple. What is the PDF of the exponential distribution? This is my PDF of the exponential distribution. So that's very simple. If I consider the two arrival times at here and here, what is the time interval between them? That is a capital T. This is my inter-arrival time. So if I consider the EIs is occurring at the time Ti, EI plus 1 is my occurring at the time of Ti plus T. Then the inter-arrival time between them is my capital T, which is a continuous random variable. So we can start from here. What is the meaning of that? T is greater than of here. That means because EI plus 1 is occurring at here and EI is occurring at here. So what is the meaning of this? EI plus 1 did not occurring in this interval. Why? Because EI is occurring only at this point. So in between them, EI plus 1 does not occur. Or you can say no arrival in the occurring of T of 0 plus 1. So whenever there is no arrival, what is the meaning of that? It is nothing but my of here. So what is the result of this? By using the Poisson process, because by using the Poisson process of here, we can substitute n is 0, we will get this expression. Now we can define the cumulative distribution function. I can write this function as greater than of t. I can substitute this value which is written by here. We can take the derivative, we can define the PDF. What is the PDF? How you can define the PDF of from the CDF? By using the derivative. So clearly say that it follows the exponential distribution. Last concept is that is the arrival time. What is the arrival time is if you have the inter-arrival times of the n1, n2 and so on. Meaning is if you consider say this is 0, then this is the first inter-arrival time. This is my say T2, or you can say this is my T1, this is my T3 and so on. So this is my length, this is n1, this is the length L2 and this is the length n3 and so on. And the last result say this is the inter-arrival time and it follows the exponential distribution. Then the arrival time is the cumulative sum of this. That is the arrival time is the first arrival occurring at n1, second is here and then so on. We all know ni follows the exponential distribution. Then the sum of the exponential distribution will follows the gamma distribution. We all knows that. So that means Ti will follows, or you can say T of n will follows the gamma distribution. So once it's a gamma distribution, the PDF is my here. Or clearly says that these arrival times are not independent. Why? Because clearly says that T1 is less than of T2, both are dependent on each other. That means whenever you have the Poisson process, arrival time will follows the gamma distribution, while the inter-arrival times follows the exponential distribution. And how you can find the mean of this? So clearly says that how you can find the mean of Tn, that is nothing but my mean of Ti. So but Ti's are Ni, but Ni's are inter-arrival, so it follows the exponential distribution. Exponential distribution has a mean 1 by lambda. So what is that? This is n over lambda. Similarly, you can compute the variance. So look at the one conclusion example related to all these four concepts. What is given to you? Nt is my Poisson process with the intensity rate is my 2. Xi's are my inter-arrival times. So what is the meaning of that? It means Xi's follows the exponential distribution with the intensity rate 2. This is given to you for all I, 1, 2 and so on. Find the probability, the first arrival. So look at that, the first arrival, that is my T1. This is arrival after 0.5. This is the first requirement for you. But we all know that what is a T1? This is nothing but my arrival. So in this case, arrival is my x1. So it means x1 is my greater than 0.5. This is my required target for this first problem. So here, and we have derived that it is greater than of this, so we can start, or the first method is we can start from here. We can substitute lambda is my 2, t is my 0.5, so this is the right answer. Or we can use the exponential distribution. So since xi follows the exponential distribution, I can write this in terms of the CDF, which is less than of the 0.5, which is nothing but my 1 minus f of 0.5. What is the CDF of the exponential distribution? The CDF of the exponential distribution is 1 minus lambda of x. So I can substitute this value. 1 minus x is my 0.5. So which is here, you can see 1 and 1 will be cancelled out. E raised to power minus 1 is the same answer. Look at the second part. find the probability x is greater than 1, that is the inter-arrival, when there is no arrival before the time t1. No arrivals, again there is a t1, but t1 is nothing but my x1. So no arrival, that's a condition, that's it, means the conditional probability, no arrivals occurring before t1, that is all arrival occurring here. So how this is the conditional distribution, xi follows my exponential distribution. And what is the property of the exponential distribution? It is my memoryless property. What is the memoryless property? Is whenever x is greater than of the m, x is greater than of the n, then it is always be greater than of m minus n. So I can write this number as x1 greater than of 3 minus 1 is 2. That is a memoryless property. So again we can use this concept. What is the probability of x greater than t in the exponential distribution? This is my here. So e raised to power minus of 2, t is my 2, e raised to power minus 4 is the right answer. Look at the third part. If the third arrival occurring at 2, that is a t3, this is my occurring at 2. What is the meaning of that? x1, x2, x3, this is given to you. Find the probability that the fourth arrival occurring after the t4. So fourth arrival occurring after the 4, this is my condition. That is the requirement for you. Now what is the meaning of that? Since inter-arrival times are my independent, so since each of the xi's are my independent, so what is the probability of A condition B when it is of the independent? That is the probability of A only. So we can write like of this one. So because of independence, now again we can use this concept of here. Look at the last one. If capital T is the first arrival after the time t, so what is the meaning of that? This after the time t is my here. So you have to find the mean of t and the variance of t are here. How you find the mean of t? So that is a mean of 10 plus x. So 10 is a constant which is outside, mean of the x. X is my exponential distribution. What is the mean of the exponential distribution? Is 1 by here. What is the variance of the exponential distribution? Is 1 by lambda square. So lambda is my 2, so it is 1 by 2, that is 21 over 2. What is the variance of t? Variance of the constant value is 0, so variance of x, it is a 1 by 4.25 is the right answer. So this is the way you can solve this simple method. We will see the next lecture some more examples related to the Poisson process, how we can solve it. I hope you can simply learn this concept. Till then you can simply like, share and comment on my videos. Best of luck students. Happy learning.